In this video, we're going to begin our discussion of formal operational semantics. Just as we did with lexical analysis, parsing, and type checking, the first step in defining what we mean by a formal operational semantics is to introduce the notation. And it turns out that the notation we want to use for operational semantics is the same or very similar to the notation we use in type checking. We're going to be using logical rules of inference. So in the case of type checking, the kinds of inference rules we presented prove things of the form that in some context we could show that some expression had a particular type, in this case the type C. And for evaluation, we're going to be doing something quite similar. We will show that in some context, now this is going to be a different kind of context than we had in typing. So this is going to be an evaluation context as opposed to a type context, and so what goes in the context will actually be different. But for the moment, all that really matters is there's some kind of a context, and in that context, we're going to be able to show that some expression evaluates to a particular value v. So as an example, let's take a look at this simple expression, e1 plus e2. And let's say that using our rules, which I haven't shown you yet, but let's say we had a bunch of rules, and we could show that in the initial context, that e1, in that same context, okay, so these contexts are going to be the same, that e1 evaluated to the value 5, and e2, also in that same context, evaluated to the value 7, then we could prove that e1 plus e2 evaluated to the value 12. And if you think about it, what this rule is saying is that if e1 evaluates to 5 and e2 evaluates to 7, then if you evaluate the expression e1 plus e2, you're going to get the value 12. And now what's the context doing? Well, it doesn't do a whole lot in this particular rule. But remember what the context was for in type checking. The context was for giving values to the free variables of the expression. And so we need, for an expression like e1 plus e2, to say something about what the values are of the variables that might appear in e1 and in e2 in order to say what they evaluate to, and therefore to say what the entire expression e1 plus e2 will evaluate to. Now, let's be a little more precise about what's going to go in the context. So let's consider the evaluation of an expression or a statement like y gets x plus 1. Okay, so we're going to assign y the value x plus 1. And there are two things that we have to know in order to evaluate this expression. First of all, we have to know where in memory a variable is stored. So for example, the variable x here, we're going to have to go and look up x's value and then add 1 to it. And then that value is going to have to be stored in whatever memory location holds the value for y. Okay? So there is a mapping from variables to memory locations. Okay, and that is called, in operational semantics, the environment. And this is a little confusing maybe because we've used environment for other things. Okay, so now let's forget about those other uses of the word environment. When we're talking about the operational semantics, what the environment means is the mapping, the association between variables and where that variable is stored in memory. And then, in addition, we're going to need a store, and that's going to tell us what is in the memory. So just knowing the location for a variable isn't quite enough. If we know the value of x, if we know the location for x, for example, well, that's important because that's where we're going to get the value of x, but we also have to know exactly what value is stored there. And so a store is going to be a mapping from memory locations to values. These are the values that are actually stored in the memory. So it's two levels of mapping. We associate with each variable a memory location, and then each memory location will have a value in it. So now let's talk about the notation that we're going to use for writing down the environment and the store. So as we said, the variable environment maps variables to locations, and we're going to write that out in the following way. We're going to just have it as a list of variables and location pairs separated by a colon. So this environment, for example, says that variable A is at location L1 and variable B is at location L2. And another aspect of the environment is that it's going to keep track of the variables that are in scope. So the only variables that will be mentioned in the environment are those that are currently in scope in the expression that we're evaluating. Now, as we said, stores map memory locations to values, and we'll also write out stores as lists of pairs. So in this case, the memory location L1 in this store contains the value 5, and the memory location L2 contains the value 7. And we will also separate these pairs by an arrow, just to make the stores look a little bit different from the environment so that we won't confuse the two. There's an operation on stores, which is to replace a value or update a value. So in this case, we're taking the store S, and we're updating the value at location L1 to be 12. And this defines a new store S prime. Okay, so keep in mind here that stores are just functions, at least in our model. And so we can define a new store by taking the old function, the old store S, and modifying it at one point. So this defines a new store S prime, such that if I apply S prime to the location L1, I get out the new value 12. And if I apply S prime to any other location, any location different from L1, I get out the value that the store held in S. Sorry, I get out the value of the location in store S. Now in Cool, we have more complicated values and integers. In particular, we have objects, and all the objects, of course, are instances of some class. And we're going to need a notation for representing objects in our operational semantics. So we'll use the following way of writing down objects. An object will begin with its class name, in this case the class name X, and it will be followed by a list of the attributes. Okay, in this case, the class X has n attributes, A1 through AN, and associated with each attribute will be the memory location where that attribute is stored. So attribute A1 is stored at location L1 up through attribute AN, which is stored at location LN. And this will be a complete description of the object, because once we know where in memory the object is stored, we can use the store to look up the value of each of those attributes. There are a few special classes in Cool that don't have attribute names, and we'll have a special way of writing them. So integers only have a value, and that will just be written as int with a single value in parens, the value of the integer. Similarly for booleans, they have a single value, true or false. And strings have two properties, the length of the string and the string constant. There's also a special value void of type object, and we'll use the term void in our operational semantics to represent it. And briefly here, so void is special in that there are no operations that can be performed on void except for the test is void. So in particular, you can't dispatch to void even though it has type object. That'll generate a runtime error. The only thing you can do is to test whether the value is void or not. And concrete implementations would typically use a null pointer to represent void. Now we're ready to talk about in more detail what the judgments will look like in our operational semantics. So the context will consist of three pieces. The first piece is the current self object. The second piece is the environment, which is, again, the mapping from variables to the locations where those variables are stored. And the third piece is the memory, the store, the mapping from memory locations to the values held at those locations. All right, so in some context, an expression E will evaluate to two things. First of all, E will produce a value. So for example, we saw before that the expression 7 plus 5 would produce the value 12. That's one result of evaluation. But the second thing is that it will produce a modified store. So the expression E may be a complicated piece of code, maybe a whole program in its own right, and it may have assignment statements in it that update the contents of the memory. And so after E has evaluated, there will be a new memory state that we have to represent. And so S prime here represents the state of memory after evaluation. So now notice a couple of things here. First of all, the current self object and the environment don't change. They are not changed by evaluation. So which object is the self parameter and to the current method, And the mapping between variables and their memory locations, that is not modified by running an expression. And that makes sense. I mean, you can't update the self object in cool, and you don't have access in any form to the memory locations where variables are stored. And so those two things are invariant. They're invariant under evaluation. They don't change when you run a piece of code. However, the store does change. So the contents of the memory may be modified. And so that's why we need a store for both before evaluation and after evaluation. And one more detail, these judgments of this form always have a qualification that the judgment only holds if the evaluation of E terminates. So if E goes into an infinite loop, then you're not going to get a value and you're not going to get a new store. So this kind of a judgment should always be read as saying that if E terminates, then E produces a value V and a new store S prime. To summarize, the result of evaluation is a value and a new store, and where the new store models the side effects of the expression. And notice again that some things don't change as a result of evaluation, and this is actually important for compilation because we'll be able to take advantage of the fact that they don't change to generate efficient code. So the variable environment doesn't change, the value of self, which object we're talking about, doesn't change. And notice here, as another detail, that the contents of the self object, the attributes inside the self object might change. They might get updated, but the locations where the attributes are stored do not change. So the layout of the object, where the object is stored, doesn't change, and that's all we're saying here. The actual contents of the object, which of course are part of the mapping of the store, those might get updated by evaluation. Okay? And also, the operational semantics allows for non-terminating evaluations. That's the last point here. And so meaning that those judgments only hold on the assumption that the expression actually completes.